Okay. Yes, so hello everyone. My name is Oleksiy, and I will talk about our recent work called Continual Learning with Foundation Models. So this is a joint work with my colleagues Timothee, Paul, Rifat, Arthur, Irina, and Laurent. And in recent years, we all have witnessed this development of larger and more general models, the so-called foundation models. And the main promise of these models is that they can produce this meaningful features that can be meaningful for a wide range of tasks. And so the main question that we ask in this work is, how can this impact continual learning? So if this promise of these models is fulfilled, then we can even maybe sidestep continual representation learning, at least in some cases. And so this is exactly what we're doing in our experimental setup here. So we are simulating this extreme situation by replacing the usually continually trained feature extractor by a fixed pre-trained model, of which we test around 30 different models. And so during the continual learning phase, we're just training a small classifier on top of these encoded features. So this is essentially doing continual learning in the latent space of these large pre-trained models. And so on the classifier side, the classifier can be, for example, a MLP, which is the baseline we call latent ER, because we're using experience replay, but in this case, it will be latent replay. We can even use a simpler model, which is a distance-based classifier like NMC or SLDA as another baseline. And we also have the baseline that we called end-to-end ER. So this is standard continual learning where we train end-to-end both the classifier and the feature extractor and do raw data experience replay. So in all experiments, we are in the single hat setting, and we're doing class incremental here. And if needed, we're using replay to prevent forgetting. We choose replay just because of its generality and the applicability to class incremental setting. And so maybe to highlight the utility of this setup first, well, the utility of this setup for maybe research comes first because of its computational efficiency. So you can really run a lot of experiments here because you only have to train a small classifier continually. And the second reason for this setup being useful for research is that we can produce diverse set of data streams. So what I mean is that if you have, let's say, 5 raw data streams, and let's say you have 30 different tools, you can encode these 5 data streams with 30 different models, and you will get like 150 different streams. And each of these streams has different, will result in different dynamics in terms of forgetting, transfer, and interference, because the task relationship in these streams are different. So the task similarity is different. The tasks have different complexity, let's say, not complexity, but they're different hardness. All right, so we have this question: to which extent can we sidestep continual representation learning? This model, but more specific goals here are also to highlight the utility of this setup, Latent CL, which I just did. Also, we would like to study interference, transfer, and forgetting from the data perspective, because this setup gives us so many streams, so we can only vary the input data stream and keep the algorithm fixed. This is exactly what we're doing. And we are also interested in studying how the relationship between upstream and downstream data, as well as how different pre-training regimes impact the final continual learning accuracy. Okay. All right, so maybe to make the long story a bit shorter, one of the conclusions that we had, and maybe something that is rather unsurprising, is that really one of the main factors that's important when trying to answer this question, whether we can sidestep continual representation learning, is really the relationship between the upstream and downstream data. So for this reason, in most of the experiments, we distinguish between 2 types of streams, the in-distribution and out-of-distribution streams, and this is with respect to the pre-training data. All right, so now I would like to talk about a subset of our experiments. So first, the biggest advantage of doing latent continual learning is the compute, but the disadvantage is the reduced flexibility of the model because you're fixing the feature extractor. So there is this trade-off between compute and accuracy. And so in this plot, we present the consolidated view of this trade-off, where we compare the latent ER, which is in orange, and end-to-end ER, which is in blue. And so we show that, yes, in distribution situation, there is basically no difference between these two regimes. And in out-of-distribution situation, to-end fine-tuning with raw data replay works better, as expected. So maybe one possible conclusion from this is that as these foundation models become better, we're more likely to end up in this in-distribution situation where doing end-to-end continual learning is maybe not that useful in terms of accuracy, at least. And latent ER, of course, has a much better compute properties. And so maybe driving this a bit more to extreme, if you already have a good feature extractor, then there is really no need for continual learning anymore. Why is that the case? Because you can just simple metric-based classifier on top of your feature extractor, and such a classifier doesn't have forgetting by design, so you don't need replay there. So this is something we also compared, or we tried to show in these plots. So in these plots, we have the metric-based accuracies as horizontal lines, and the more powerful MLP classifier is the curved line, and on the x-axis are the different replay buffer sizes. So for small replay buffer sizes, the more powerful MLP underperforms the metric-based classifiers. This is because it has forgetting, but for larger replay buffer sizes, it outperforms MLP-based one outperforms the metric-based ones. And for in-distribution stream, the advantage of the more powerful MLP-based classifier is really small. Okay, so I said that we need a good feature extractor to be able to sidestep continual representation learning. So how do we get a good feature extractor? One obvious solution is, of course, to make your pre-training data broader, so pre-train on more data. And yes, this works. Also in our experiments, we can confirm this, that the broader your pre-training distribution, the more likely you are to have higher continual learning accuracy. And in our experiments, the CLIP models, they work the best on average, slightly better than the others. But that's for in-distribution situation. So what if you're in out-of-distribution situation? In out-of-distribution situation, it seems that the pre-training regime has an important role. So here, for example, having a self-supervised pre-training worked better than having supervised pre-training, even though the amount of pre-training data in the supervised case was smaller. And okay, so we said that we have good feature extractor, then the final continual learning accuracy will be better. But why is it the case? Is it really just because your per task accuracy is higher? That's definitely part of the story, but you could still have catastrophic forgetting, and which would result in your final CL accuracy still being very bad. So is it because there is less forgetting maybe or less interference in the in-distribution case? And so we leveraged the advantages of this latent CL setup, where we took a data perspective, we were our models using many different input streams. And so indeed, on average, we observed that there's less forgetting in the in-distribution case, as well as less interference. So it's also important to mention some other results that we have in our paper. We looked also at task similarity, and we tried to link the good performance of the model in the in-distribution case also to the task similarity. We looked also at how transfer and interference evolve as you change the replay buffer size. We also looked at ensembling and if ensembling representations coming from different feature extractors. And so to conclude, we showed that data plays an important role in continual learning, and we think it's a promising research direction to study how data impacts the final continual learning accuracy. And we think that latent CL setup can be useful for that, because we can generate so many streams, and we can our experiments will be very compute efficient. Regarding the question whether we can sidestep continual representation learning, it really depends on the relationship between your downstream and upstream data. So if you already have a good feature extractor, then maybe yes, because you can just train a metric-based classifier which will have no forgetting by design, so to say. In short term, we can further improve the performance of latent ER baseline by, for example, ensembling representations, doing domain-specific pre-training if possible, or using data-dependent metrics like task similarity, for example, for improving our algorithms. And in long-term perspective, we think that it's important to acknowledge this trend. It may be the case that this development of large-scale pre-training will result in potentially sidestepping the problem of representation learning, and promising research directions could be, for example, developing algorithms for pre-training that are good for the downstream continual learning, or also developing algorithms for fine-tuning of these large models without losing their ability to generalize to many different tasks. Thank you very much for your attention.
Any questions? What's the best foundation model that you used?
Oh yeah, it was the best foundation model that we used. It was CLIP model, like the largest CLIP model was the best, I think.
Thanks. So we talk layers to labeling points as we were to
Could you repeat, please?
It also tries different layers to use the certain features and see if it does error.
Yes, we tried. So the question is whether we try to ensemble or even not ensemble, but just take the features from different layers of these large pre-trained models and see if they generalize better. Yes, we did, and there is no large improvement. So we did something similar to what Head-to-Toe does, where they ensemble features from different layers. However, we did not do any sparsity regularization. So maybe the sparsity regularization, which was part of Head-to-Toe, would improve the results further, but just simply ensembling those didn't help it much. Yeah.
If there are no other questions,